Hello everyone, my name is Rick Costello and welcome to the universe we live in, which is just a great place and we're lucky to be here. But here we are as I'm standing on the moon and kind of dancing on the moon, and look at our Earth back there about 250,000 miles away from me right now. And our Earth is about 7,900 miles in diameter. Pretty small place when you think about it, and it has everything we need to live, and we have to keep it that way because we're kind of responsible for it since we are the species of the Earth, the number one species. And now in the last two shows, I talked about small red dwarfs and then the sun. And here we have a photograph of TRAPPIST-1 compared to our sun. And TRAPPIST-1 is about 84 times the mass of Jupiter. And the smallest stars can be around 80 times the mass of Jupiter. If Jupiter had about 80 times more mass, being basically a big ball of hydrogen and helium, it would become a mass, but it's about 80 times less mass than a star needs. And so this TRAPPIST-1 is about 40 light years away from us, and being one of the smallest red dwarfs, they fuse their hydrogen to helium, very slow rate, and they use all the hydrogen within the star. And TRAPPIST-1 will live for about 12 trillion years, which is a credible amount of time. When you think that just 1 trillion years is 1,000 billion years. So here we're talking 12 trillion of those. Or 12 trillion years, and it'll be fusing hydrogen to helium. Now this next slide is another red dwarf, the closest star to us, Proxima Centauri, and Proxima Centauri is about 4.2 light years away from us, 4.2 I should say, and it's about 129 times the mass of Jupiter. And it'll live for about 4 trillion years, fusing hydrogen to helium. Now this next slide, we get into the sun, and we talked about stars like the sun, and stars like the sun, their mass goes up to about 8 times the mass of the sun, and they're basically they'll be fusing the hydrogen to helium, and eventually the helium into carbon, and the sun will last for about 10 billion years, and then after it starts fusing the helium to carbon, the sun is going to expand into a red giant, like this next slide. And there we go, and it's going to swallow the orbits of Mercury and Venus, and probably the Earth too. It's going to grow pretty large, our sun, in this red giant stage. And on this next slide, we show you what happens afterwards, which we talked about in the last show. And when the sun starts going into the red giant stage, it's going to be so large that the gravity from the core of the star isn't going to be able to hold on to the outer layers. And the solar wind is pretty much just going to blow the outer layers off the star. And that's what you see in these couple other slides of these nebulas. And there's a ring nebula there, the remnants of the outer layers of a star. And in the center of that, we have a white dwarf star, basically a giant ball of carbon and some oxygen. And here we go on this next slide. And this shows you the size of that white dwarf star. Like I said, basically just made of carbon and nitrogen. A little bit bigger than the Earth. It'll be the sun, the core of the sun, when this is finished. Now in this next slide, we get into the red giants, the giant stars of the universe. And these stars can be, tens of times heavier than the sun, or more massive than the sun, up to a couple hundred times the mass of the sun. And here we'll start with Betelgeuse here. Now Betelgeuse, you see the fourth star up there, it's about 16 times the mass of the sun. Its diameter is about 600 million miles. I mean, consider the Earth, which is about 93 million miles away from the sun. This is a huge star. And it's in the red giant stage, and probably another 100,000 years or so, the core is going to turn iron, and it'll blow itself up in a supernova. We had thought recently, this past summer of 2020, that maybe Betelgeuse was getting ready to go supernova. As it was dimming, it seemed like it shrank, and we thought it was going to pulse and blow up. But it turns out there's one of two things that happen. We're not really sure. Some scientists believe that Betelgeuse threw a shock wave of material out, and that was blocking the light from Betelgeuse from reaching us, and that made the dimming. Others have suggested that maybe Betelgeuse has a giant sunspot on it, and that sun being dark is not allowing as much light to reach us. But we're not really sure what's going on with that. But it's still pretty stable right now, and another 100,000 years before it blows itself up in a supernova, which is too bad because I was hoping it was going to happen soon because it would have been just a great sight to see in our sky. And then we have above Betelgeuse, we have the Pistol Star, which is about 27 times the mass of the Sun, and its diameter is about 376 million miles in the red giant stage. It's going to live for about 7 million more years, ending in a supernova. And then above that we have, or to the left of that, we have the giant star UY Scuti, one of the largest stars in the universe that we've found so far. And it's about 7 to 10 solar masses, but its diameter, it's in the red giant stage, so it's blown up there, and it's about 1.4 billion miles in diameter. It's a super large stars, and we've actually found a few stars larger than this. One of them right now, the most massive star, like UY Scuti, it's one of the largest stars, but it's got 7 to 10 masses, so it's not a huge mass star. But the largest mass star we found so far is a star named BAT, B-A-T 99/98. It's about 226 times the mass of the Sun. It's a huge mass star. It's about 32 million miles in diameter. It hasn't gone into the red giant stage yet. But eventually it will, and probably blow itself up in a supernova, or could collapse right into a black hole. These giant stars with hundreds of times the mass of the star. And so here we look at one of my favorite constellations up in the wintertime. It's up this time of year right now, as we're filming this in December. It'll be up throughout the winter. And it's the constellation Orion. And when we talk about big stars, the massive stars, there's a lot of massive stars in the Orion constellations. That's why I picked this one. Now, as we look around here, we have a few of the stars. One of them up here is this bright one up here. That's Bellatrix. And Bellatrix is about 243 light years away from us. It's about 9 times the mass of our Sun. Very massive star. And then below here, on the bottom here, below, if I go way down here, this star way down there, excuse me, that's the star Saiph, spelled S-A-I-P-H. And it's about 700 light years away from us, and about 15 times the solar mass. Its diameter is about 22 times the mass of the Sun. A very giant star. Now, on these next slides, we'll point to some other stars. We have Betelgeuse here, the red giant we were just talking about. And again, it's about 548 light years precise now. And it's actually a little bit closer than we thought it was a few months ago. We thought it was over 600 light years. But now we think it's about 548 light years. And again, about 16, somewhere between 15 and 20 solar masses, and a diameter of 660 million miles. And on this next slide, another giant star is the star Rigel. And Rigel is about 860 light years away from us, 21 solar masses, about 21 times the mass of the Sun, and its diameter is a little over 68 million miles. I know, and there you go there with Rigel. And here we are, Mintaka, the top star of the 3 stars of Orion's belt. And these stars, even though they're bright in our sky, they're very far away. And this star, Mintaka, 919 light years away from us, a massive star, about 20 times the mass of the Sun, solar masses here, and the diameter a little over 14 million miles, a massive star. And it's still not in the red giant stage. I mean, it's a large star. And the next star of Orion's belt, we go to the middle star, Alnilam. And Alnilam's about 1,359 light years away from us. It's a giant star, about 40 times the mass of the Sun, and its diameter is a little over 22 million miles, another massive star. All these stars are pretty massive. This next slide is the last star, the bottom star of the Orion's belt, Alnitak. Now Alnitak's, as you see here, about 826 light years away. It's about 20 solar masses, and its diameter 17,200,000 miles in diameter. Another massive star, and all these stars are going to blow themselves up in supernovas eventually. Not for a while. They're pretty young, but they're not going to live for very long. Only a few million years compared to the billions of years our sun or smaller stars will live. Okay, and here we're going to talk about what's happening inside these stars, in the core. And I'm just going to move over here so you can see at the other side of the screen. And as every star begins, the core begins fusing hydrogen to helium. And eventually the core is going to turn to helium, and then the fusion is going to stop, and gravity is going to crush that core, start building up temperatures to about 100 billion degrees. And then the core is going to start fusing the helium into carbon and oxygen. And meanwhile, the red line around the core, that layer around the core, that hydrogen in that layer is going to be hot enough to start fusing that hydrogen into helium. So you start getting double layers here of the core fusing helium to carbon and nitrogen, and then around the core you get an envelope fusing hydrogen to helium. And then once that stops, the next phase on the next slide here, once the core does turn to carbon and oxygen, or carbon and nitrogen, I mean, the core, when it fills up with finishes fusing the carbon and nitrogen, its fusion is going to stop, and again the core is going to crush. Gravity is going to crush the core, building up the temperature, even higher temperature, and now the core is going to start fusing the carbon and the nitrogen into oxygen. And then now you see around the core here, you see these double layers. Now the red layer around the core, that's going to start fusing the helium into carbon, and then the green layer around it, that hydrogen is going to start fusing the helium. You start getting this envelope building around these cores, and eventually the core is going to turn to oxygen, and with that time the fusion is going to slow down. Gravity is going to crush that core, building the temperatures up even higher. And on this next slide, we start seeing the core fusing the hydrogen into neon. And then you have these other layers around. The red layer is going to be fusing the carbon to oxygen, and the green layers, the bluish layer is going to be fusing the helium to carbon, and the outer layers is that hydrogen is going to start fusing to helium. And again, once the core turns to neon, after fusing the hydrogen, again the core is going to stop. The fusion is going to stop. Gravity is going to crush that core even further, building up the temperature again, and then it'll be hot enough, on this next slide, it'll be hot enough to fuse the neon into magnesium. And then you have these outer layers, the layer around the core, that's going to start fusing oxygen to neon, and then the layer beyond that, carbon to oxygen, the layer beyond that, helium to carbon, and then another layer around that, hydrogen to carbon. And then once the neon core does turn all to fuse to magnesium, again the fusion is going to stop. Gravity is going to crush that core even further, building the temperatures up. And in this next slide, you'll see the magnesium is now going to turn to silicone, and you get all these other layers around the layer next to the core, neon to magnesium, and the layer beyond that, oxygen to neon, and the layer around that, carbon to oxygen, then helium to carbon, and the outer layer again, hydrogen to helium. And again, once that magnesium core turns to silicone, the gravity is going to, the push outward from the heat is going to stop, the fusion is going to stop, gravity is going to crush that core even more, and next, on this next slide, it's going to start fusing the silicone into iron. And then you have all these other layers around the star. And you can go on this next slide. Here we go. And this is what's going to end up. I'll move back over here so you can see this. And what we end up is like an onion inside the star, different layers fusing different elements. And some of these elements are going to end up, to make planets again. But eventually, when the core turns to iron, the fusion is going to stop because you need temperatures in the trillions of degrees to fuse iron together. And And that cannot happen in, in the core. And so if we go on this next slide, and so on this side, it shows you what's going on in the sun. You have the pressure from the heat pushing the star outward, and at the same time, gravity's pulling the star in. And eventually, when the core does turn to iron, the fusion is going to stop, the core is going to start to cool, and eventually it's going to reach a point where that gravity is stronger than the push outward from the heat. And when that happens, in a split second, this core is just going to collapse. Boom! It's just going to collapse. And we go on this next slide here. And then you have a supernova. And what happens is you have the core. If you can go back to that last slide, Mike, if that's possible. Yeah, I just want to go back here. Now, around the core here, when it does collapses, everything's going to start moving into the core. The whole star is going to start moving in. And when it's going to bounce off the core, then you have, when the core collapses, when that iron is broken apart in the collapse, it's going to send out a wave of neutrinos. And that neutrinos, along with a bounce off the core, is going to send a shock wave right through the star. And as the outer layers are moving in, the shock wave is moving out, and they hit each other. And that creates temperatures in the trillions of degrees, and that fuses all the layers in the outer layers, and it fuses all the elements into higher elements, all the way up to uranium. And as this next slide shows, a supernova happens. And it blows itself up, and it throws all that mass, all those new elements out into the galaxy. And now you have all the elements to make everything from planets, air, water, and us, life itself. All the atoms in our bodies, the iron in our blood, the calcium in our bones, the phosphorus, the oxygen that we breathe, everything that makes us, everything that makes all the rocks and the air on the earth, all the moons of the solar system and the planets, all those elements came from a supernova from stars like this. And we figure about 2 or 3, we're probably a third generation star, which means 2 giant stars blew themselves up, making all this new matter, these new elements, throwing out in space, and then they recongest. Another giant star blew itself up, adding to that collection of new elements, and then our star was formed from those elements inside a giant cloud, molecular cloud in our galaxy, mostly hydrogen. But now you have all these other elements mixed in with it, and now you have the opportunity to make planets and eventually life like us. And on this next slide, it shows you some supernova remnants here, just blowing itself up. And again, all the elements to make everything are in these explosions. And there's another slide here. This is a Crab Nebula, which is actually just above the Orion constellation. Nice thing to see through a telescope. And again, a exploding star, and these are the remnants of it. And it's spreading out through space. Within the galaxy, and again, like I said, it'll mix with more elements and more hydrogen to fuse later on, billions of years from now, to form new stars, and now you have the elements to form planets too. And this next slide, there's another remnant there, and again, just all throwing out the mass into the galaxy. Now this next slide is the last one. There's Tycho's explosion they saw. This you can really see all the mass in there, all the elements, the atoms and molecules in this blowing out to space. All right, in this next slide. Now this is the Whirlpool Galaxy, and recently, this past year, we've had a supernova. And if you look at the galaxy, and if you look in this one, right about there, let me go back here, right about here, there's no star there. But as we move back here, we can see right here there is a star. And that's a supernova. It just happened, blew up in the Whirlpool Galaxy. And the Whirlpool Galaxy is located just under the last star of the handle of the Big Dipper. And so there's a supernova happening here. And these things when they blow up, they're as bright as billions of stars. They can be brighter than all the light from all the stars in the galaxy. And there's a massive star there. And on this next slide, we go to Andromeda. We'll just show you a couple of galaxies here. And you see all the clouds of atoms in here. In this next slide, you see another galaxy with a lot of star-making clouds here, not a lot of nebulas and all that. In this next slide also. Now this is a galaxy pretty similar to what we think our galaxy looks like. It has this bar in the middle. We call ourselves a bar spiral galaxy. And our galaxy We used to think our galaxy was about 100,000 light years across. Now we believe our galaxy is about 170 light years across. Our galaxy got a little bit larger in the last couple of years from new observations through telescopes, as we can see through some of the gases and dust blocking our view from the outer ranges of our galaxy. And so here we have the periodic table here, all the elements from hydrogen all the way up to some man-made elements on the bottom here. But up until, all these elements from helium all the way up to uranium with 92 protons. And again, protons determine what element it is. Iron has 26 protons, carbon has 6 protons, and so on. But up to 92 protons, uranium, those are all made inside of stars, all the natural elements. They blow up, like I say, when the stars blow themselves up, they throw it out in space, and now you have the elements to make planets and stars, and eventually over billions of years, if those planets are livable, maybe we have intelligent life, or some life anyways, which I'm sure we'll find in our galaxy and probably in the universe also, probably lots of life eventually. So that's what's, like I said, everything that makes us was made inside of a star. So we are, in essence, like Carl Sagan used to say, we are children of the stars. The stars give us life, and so basically they're our old relatives. Now here we're going to go back to this, and I'm just going to talk about the core now, what happens to the core when a star explodes. When that core crushes, you have iron, which is of course made of protons, neutrons, and electrons. When the core crushes, that the electrons are actually pushed into the neutrons, are pushed into the protons, and then those protons get a little bit more mass and they become neutrons themselves, and the core just collapses until, on this next slide, we have a neutron star. And this will, that core will collapse to maybe 10 or 11 miles in diameter. And you see these two jets coming off it, and those are gamma ray jets as that rotating neutron star spins. It's a lot of energy, and it's shooting these gases of gamma rays out. And these things, 11 miles in diameter, these neutron stars are roughly, and they can be spinning tens of times per second to up to over 1,000 times per second. This is amazing, 11-mile-an-hour sphere spinning thousands of times. It's, just incredibly fast for these neutron stars. And these neutron stars eventually will cool, and you basically have a ball of neutrons, and very dense, one of the densest materials in the universe is a neutron star. Those neutrons are packed so tight together. Now for a little bit more massive stars, on the next slide, we get black holes. And that's when you have the neutron star, but it's got enough mass where the gravity's strong enough to crush the neutrons. And it basically breaks those apart, and basically it turns space inside out. The gravity's so strong, it bends space inside out, and you end up with a black hole. And the black hole, there's two thinkings on it now, that it basically crushed to a tiny point, and then around that point would be the event horizon, where the gravity is so strong around that point that even light can't escape. And stars can become black holes. The center of our galaxy, we know there's a massive black hole with about 4 million times the mass of the sun, a huge black hole. But some galaxies have the black holes at their centers have masses, billions of times larger than the mass of the sun. So these things can grow very large. But the solar black holes are obviously much smaller than the galactic black holes. And so you have a black hole here and another one here. This is an actual photograph of a black hole, and you can see the event horizon, the black, then you have this yellow and red going around it, and that's materials rotating around the black hole, and it's being heated up to super high temperatures as it's whipping around super fast around that black hole, building up the temperature, and that's how we can see this black hole as material falls in and orbits the black hole. So you have a black hole there, and that's what happens to the massive stars. Now this next slide, and this is what can happen to even more massive stars. We figured, some scientists figured like you need at least 100 times the mass of the sun or larger. But here's a star here. On the left-hand side of the slide, you see the star, and on the right side, you don't see a star. And in between there's no supernova. This star just disappeared. And this star has about 40 times, or had about 40 times the mass of the sun. And we thought that was a little too low of a mass to happen, but for some reason it happened to this star. And so they may have to rewrite some of their theories, because this 40 solar mass star going would happen to this star. But I'll explain what happened to this star. What happens is this star basically was there, and then the whole star collapsed into a black hole. There was no supernova explosion. Basically, right into a black hole. The whole star just sucked into the black hole, and it just disappeared, as you can see on the right here. And so that can happen to the more massive stars of the sun. So this, and we go to this next slide here. And I'm going to end up with a photograph of one of my paintings of our galaxy, a section of our galaxy. So that's what happens to the lives of stars, the giant stars. And we owe our existence to the giant stars, as they formed all the elements that make us and make the planet that we stand on, the water we drink, the air we breathe, all come from the explosions of massive stars. And we owe our existence to them. And so that's going to be the end of the show. And thank you for watching. And hopefully you'll join me again. I'd like to thank Michael Sinopoli again for producing this. Always does a wonderful job. And we'll see you on the next show. And when you ever get a chance, look up. It's a great universe we live in. Thank you.